Hi, welcome back to Blockchain Fundamentals with Bill Laboon. Today, we're going to discuss how to use cryptocurrency, and especially what we mean with different, perhaps, words. What are we actually doing on the network? So, throughout this lecture, I'm going to be using Bitcoin as an example, as it is probably the largest, certainly the largest and probably the most well-known of any blockchain technology out there, and certainly the first modern cryptocurrency. However, a lot of what we're going to discuss here can apply to other blockchains, and I will, throughout mention where it differs from other chains, or what's special about Bitcoin, or what others do slightly differently. So first off, we need to answer the question: what does it mean to own some Bitcoin? Remember, everybody has access to all of the data on the blockchain. So really, owning Bitcoin is going to involve knowing some information that lets you control some of the data on this blockchain. And specifically in terms of Bitcoin, owning it means that you have the ability to control any UTXOs that have been sent to some set of addresses, and then generate new transactions from them, which you can prove that you are the rightful owner of these UTXOs by signing these transactions with the corresponding secret keys for each address. So if this doesn't make sense, I recommend going over the exercise where we generate secret keys and signatures from them, and you can see how anyone can know your public key and thus send funds to it. However, only the person who knows the private key can send things on from that address or set of addresses. So talking about all of this sort of theoretically, we've always said that a public key, we've really just assumed it is basically an address. However, in most cryptocurrencies, including Bitcoin, although we can think in a sort of naive way that the public key is really your address, it's actually slightly more complicated than that. Your address is a function of the public key. So the public key associated with your address, to actually get the address through it, you have to go through at least in Bitcoin, you go through a rather convoluted process, which we'll cover briefly just in a few slides. So if you remember, we talked about the different kinds of transactions on Bitcoin. Generally, what you'll see in a normal transaction is a P2PKH, pay to public key hash, not a straight pay to public key. For an ordinary user of Bitcoin, you will probably never see the general public key. So other network systems actually can take advantage of this. So for instance, in Polkadot and Kusama, these two there are two separate networks, but you can make an address for them based on the same public key. So you could use the same public and private key pair and create a Kusama address and a Polkadot address. And these addresses will look very different from an address perspective, what the user sees, even though behind the scenes they're really just manifestations of the same public and private key pair. In Bitcoin, these addresses are generally represented in what's called Base58Check format. So this Base58Check is just a Base58 numbering system with a few extra twists. So if you remember binary, base 2, that just has 0 and 1, two possible values. In more rare instances, you'll hear about octal, which has base 8, so things like Unix file permissions use octal, or hexadecimal, base 16, so 0 up through F. Base 58, just like these, is an extension. It has 58 possible digits, starting from 1 and ending up at Z. Now, this is case sensitive here. So capital A and lowercase a have different values. And you'll notice there are a few characters missing here. It isn't just all of the numbers and all of the letters. Specifically, capital O, the number 0, lowercase l, and I are omitted. And this is because when you're writing these down, it can be very confusing. Is this a capital O or a lowercase o or a 0? And so base 58, the simplest way to eliminate this is to just get rid of the capital O and 0. If you see something that looks like an O, you know that it's a lowercase o. Something similar happened with lowercase l and capital I, since these can be confused for 1. So if I see something that looks like a 1, I know it is a 1 and not a lowercase l or capital I. So interestingly, you'll note sort of the standard non-SegWit Bitcoin addresses are going to start with a 1, which actually means the number 0. I always thought that was interesting. Base 58Check differs from normal base 58 in that there is a checksum at the end. So the last 4 bytes are actually a checksum to make sure that you entered it properly. But we should remember that a base 58 check number is still a number, which means that we can represent it in all kinds of different ways. So you probably have seen QR codes. And QR codes, really, you can just think of them as the black and the white, just ones and zeros. And these are just another representation of a large number. So we see here a clip from a Bitcoin paper wallet here with the address 1mk ... And then that exact value also produced as a QR code. We also can produce it in decimal. So it's just a standard number, or binary, just a sequence of ones and zeros. And all of these really mean the same thing. They can be they're displayed in different ways, but all these values, the QR code, 1mk ... 557 ... 111 ... all of these represent the same thing, that public address. So we don't really have to go through all of this unless you are very interested, but I just want to show you what the process is from going from a public key all the way to an address. So first, we're going to take an ECDSA key pair. So we're going to generate this key pair, the private and public key. We'll keep the private key, then take the public key and get its SHA-256 hash. We'll then take that hash and then run the RIPEMD160 hash on that to get another value. We'll then prepend a 0 to this. Remember, this is shown as a 1 in base 58. And this just indicates it is a standard Bitcoin mainnet address. So you'll see other prefixes that indicate what network things are on. So like, if it is a testnet or a different type of address, like a SegWit address, you'll see different prefixes on it. So now that we've done this, we're going to take the SHA-256 hash of the 0 plus the RIPEMD160 hash, then take the SHA-256 hash of that. So we're going to do a double SHA-256 hash. We take the first 4 bytes of this last hash and add that to the end of the prepended address found in step 4. So what we have is now that step 4 plus, if you do a double SHA-256 hash on it, you're going to get this final result, which we can use as a checksum. Then we're going to take that original result back in step 4 and add that checksum. All right, so the first 4 bytes of that last SHA-256 hash after the double SHA-256 hash. And finally convert that result to Base58Check encoding. So you can see that part of this, the steps in italics, are just for producing the checksum. So I think this is interesting. Now anyone can just, if you want to verify that something is a valid Bitcoin address, you can always, if given that address, just run the SHA-256 hash on the value minus the checksum. Just take the checksum off, run SHA-256 on that twice, and verify that the last 4 bytes of that hash equals the checksum at the end of the address. So now we've got a way to produce Bitcoin addresses. Again, other cryptocurrencies and blockchains are going to do similar things, although it may be slightly different from chain to chain. So one of the interesting things you can do with this is generate a vanity address. So it's very difficult for me to say that I want a specific address. So if we think about this, this is really almost a variation on the proof of work that Bitcoin does. We're going to run this, this multi-hashing process on generated key pairs until we get an address that has some format of what we want. So CS1699 was my class number when I taught this course at university. So if I want to have a Bitcoin address that starts with CS1699, what do I do? Well, remember, it's very difficult, if not impossible, to figure out what the result of the hash is going to be, especially this multi-hashing process, without actually running through it. So we're going to have to run through it multiple times until we get this text that we want. So we can think of this really as a kind of Bernoulli trial. So again, very similar to mining. It's a hash. You're trying to develop a hash that gives us the right result. And there are lots of pieces of software out there that can help you do this. But just to understand how it works, again, just like mining, the easiest way to find the result should be just to keep trying with different inputs. So for every character that we want, these characters are generally random and continuously distributed. So there's a 1 out of 58 chance we'll get the correct character in that slot. So the chances that we want something to start with this are 1 over 58 to the kth power for a k character pattern. So you can imagine this would be very difficult to do and grows very quickly, right? So every time that we want to generate one more character in our vanity address, that we're going to increase the amount of time it takes on average by 58 times. Now, of course, we always could get lucky or unlucky. It's hard to say exactly how long things will take, but definitely will generally take longer the more characters you want. So I have a link to a vanity generator. There are lots of other vanity generators out there for Bitcoin, for Ethereum, for all sorts of different blockchains. So I want to show you some times here as I tried to generate CS1699 to be the first characters of my vanity address. So here you can see I tried to first have it start with 1C. So just remember, we have to start with 1 if we're generating a Bitcoin mainnet address here using the standard format. So we can see this took 0.016 seconds. Very quick. I've got, here's my private key. My address is 1C, so I started with C, and that took 16 milliseconds. 1CS only took slightly longer. And in fact, it was actually rounded off in here to the exact same amount of time. And this is because we're really not looking for that many different characters here. If we think about this, to get a C, well, on average, we'd have to do 1/2 times 1 over 58 So 1 out of every 29. So we should just be able to produce 29 addresses. That should be very simple, and a modern computer can do that very quickly. Now we can see, though, once we start looking for 3 characters, 1CS1, we're starting to get a little bit of extra time here. This took a little over half a second to give me the address 1CS1KOO, whatever. And adding another to that, 1CS16, well, now it's 23 seconds. CS169 took over 10 minutes. So you can imagine if you want a very specific address, this is going to take a very, very long time to do. I didn't actually run it, but if getting this many characters, 5 characters, took us 10 minutes, then we can imagine getting 6 characters would probably take us about 580 minutes. So multiply by 58 each time we're doing this. Again, we always could get lucky, but generally it's difficult to produce these, and the more characters you want, the more difficult it's going to be. All right, so now you've made your vanity address, if you like. You understand what an address is. So how do you store your cryptocurrency? Well, really, storing cryptocurrency is really all about managing your secret. And perhaps if you're interested in maintaining anonymity or a good level of pseudonymity, your public keys perhaps as well. But there are a variety of ways to do this. And I think the easiest way to categorize them is what trade-offs are made, because there are always trade-offs being made with how your cryptocurrency is stored. And I think the major trade-offs that we should cover here are availability. That is, how easy is it for you to access the coins there and do things with them or issue transactions from your account? Security, how secure is it? And finally, convenience. So how easy is it to deal with? So something could be very available, yet still inconvenient. So for instance, if I have to, I have something in my wallet, right? That's, however, that wallet could very easily be stolen. So it has very low security, but it's very available, but it has a horrible user interface. Well, it might not be very convenient to use. Or if I can only do certain things with it. For instance, with paper wallets, really they're send only until you sweep off all of the Bitcoin or whatever cryptocurrency from them. And so you can't really do much with them. So while they might be available, they're not very convenient. But let's actually go through some of these instances. One other thing I wanted to mention here. The big differentiation is generally between hot and cold storage. So hot storage means generally the transactions can be directly made onto the Bitcoin or whatever network, which also generally means that there is network connectivity. You're online. You can do things. Your private key is directly accessible on the same computer that the network connection is being made. So we can think of hot storage as something that's super convenient, but we can also realize that the security is not as good, because if someone breaks into your computer, then they can take your private key or send your Bitcoin somewhere else. In cold storage, transactions cannot be directly sent, so your secret keys are not connected directly to the network. The secret keys are offline. There can be various degrees of warm storage. So it might be, for instance, through a proxy. So you don't connect directly to the network, but you have a server that is only accessible through a proxy node or a sentry node. One last thing to remember, since public keys can be transmitted offline, you certainly can create something in cold storage and send it. So you may create a Bitcoin address on an air-gapped computer and just write down the the address, and then actually, people can send funds to that. They can send Bitcoin to it, but you will, even if it's offline, even if it never goes online. So you can imagine this is incredibly secure. However, there are some chains that don't allow you to do this, and the other, both the receiving and in order to receive funds, you must also be online. So perhaps the hottest and also perhaps least secure kind of wallet is having software on your computer or phone which directly keeps tracks of your keys, makes transactions, stores your coins, etc. So this is generally considered a bad idea. So while the availability is high and the convenience is very high, since it's immediately available, your computer, you're using it all the time, you don't have to pull anything out, security is extremely low. Because if anyone gets onto your computer and you're storing this, especially if you're storing this data in an unencrypted way, then anyone can get your private keys and then they will have access to all of your Bitcoin. So that's generally considered a bad thing. Paper wallets are not as popular as they used to be, especially as we've discovered some issues with them. However, this is basically just generating an address and a secret key. You print it out and just keep it on a piece of paper. You probably want to laminate this. Or otherwise keep it protected. Otherwise some water might spoil it. So here we have there are a lot of problems with paper wallets. One, they're hard to deal with, right? You can't use these by themselves to send anything. You have to have some other software which reads this data in from it. And generally it's not considered safe to be, once you read something in, to use it as a hot wallet, then that key generally is not considered safe anymore. So these can be used, if you're just sweeping a bunch of funds to them over the course of some time, and then you're moving all of it off at once. But generally, they're not considered a bad idea. They're not considered a great idea. Security can be, if you handle these appropriately, can be about medium. However, the availability, they're quite low, they're difficult to deal with, they're very inconvenient. So this should not be confused with some systems that let you write down or store your private key, a private seed phrase. So this seed phrase, which you use for hardware wallets and some other systems, can regenerate your all of the addresses that you use. However, this seed phrase is generally used in conjunction with some other system. So seed phrases are not paper wallets. We'll talk a little bit more about them when we talk about hardware wallets. But they're not, I want to make sure people understand, those are not in fact paper wallets. So brain wallets, remember that when we produce an ECDSA key pair, we're getting some randomness from the system. Well, and computers are very bad at getting actual randomness. So we, instead of that, what computers do generally is pseudo-randomly generate something, given a seed. And this seed will usually be something like the number of milliseconds since the epoch, or generate some system randomness, from like what the order that threads went in, or the key presses that you've done, or something like that. However, if we can override this seed, enter some passphrase that we remember, then run SHA-256 on that passphrase, well, we can get a new seed that lets us generate our own Bitcoin address with a private key. So this seems like really great, right? This passphrase can be entirely in your head. It doesn't have to ever go onto a computer. You can you could even calculate if you really want to, if you're really paranoid, calculate it by hand, or at least do it in an air-gapped way. However, you'll notice there's a warning about choosing a strong passphrase. And it turns out humans are horrible at coming up with enough randomness to come up with a good enough passphrase. So remember that all of this data, all Bitcoin addresses that store any funds are somewhere on the network, which means that anyone can essentially spend an unlimited amount of time trying to break them. And in fact, quite a few people have done this. They've just run different passphrases, run different sections of books or passwords or various things until they find a Bitcoin address that they now have access to. So brain wallets have the benefit of being able to be stored in your head or written down. However, using a seed phrase is going to have some other benefits that we'll discuss a little bit later. The other thing is if you have even one letter wrong here, so if you have like an extra space at the end of, when you type this in, CS6991699 is the best class ever, space or period or exclamation point, you're going to get an entirely different value here, an entirely different address. So it is really prone to mistakes, and it's hard to do things with. And it's hard for humans to come up with a good enough passphrase that it will resist, all of the attacks that can be made on this public blockchain throughout all of time. So generally, we consider brain wallets to be very low availability, very low in convenience, and generally low to medium in security. So if you do everything correctly and you can come up with a phrase or something you can remember that was not used by anyone, and you do everything perfectly correctly, it's hard for anyone else to guess, then we have medium security. But that's really hard to even get to that point. So brain wallets, not something that are really in fashion right now. So hardware wallets are kind of considered for an ordinary user probably the best trade-off between availability and security that we have. So these are generally simple devices. They tend not to be like what we would think of as a full computer, which generate keys, they sign transactions, but the secret keys never leave the device. They have very limited input and output. So transactions are fed in from your computer. They'll connect via like USB or something like that, or via just displaying QR codes. They've got very limited connectivity with the actual network. They're signed locally on the hardware wallet, and then the signed transaction is output. So basically, from your perspective, what you would do if you want to use a hardware wallet would be something like buy one of these, enter your password, run some software to send a transaction on your computer, plug in the hardware wallet to sign it, enter your passphrase or whatever on the actual hardware wallet, and then send it out over the network. So these are a little bit annoying, slightly annoying, because you need to have the actual hardware wallet with you to use it. But so that's why availability and convenience, I have it at medium. But security is extremely high, and they're not that difficult to deal with once you're just used to. It's just like carrying your wallet around. You have a hardware wallet that you have. So I remember when I first got into Bitcoin, I was thinking to myself, well, what happens when that hardware wallet fails? What happens if I dunk it into water? Or just, there's some sort of software glitch, or I get really angry at it and throw it against the wall. So generally what you can do is when you first get a hardware wallet and you generate an address, before you generate addresses rather, you can get a seed phrase fed out to you. So remember, we talked about this with brain wallets. This seed phrase is going to allow you to generate all of the data back on the hardware wallet. So if you get a new one, and these all follow a pretty standard protocol, so even if the company goes out of business, there are other ways of using the seed phrase. You then can have access to that wallet on a different hardware wallet. So you need to keep the seed phrase safe, However, this differs from a brain wallet in that the phrase is generated for you, so it's going to have a lot more randomness than something you come up with on your own. And generally, these also have checksums. So if you try to enter in an invalid word, for instance, or you have a word list that you can verify what are the particular words used. So they tend to be a lot easier and tend to be the recommended way for most users of cryptocurrency to hold their coins. So remember I said that these hardware wallets will let you produce more than one address. Some blockchains are more open and willing to use the same address over and over again. So for instance, Ethereum, in order to avoid state bloat, they really encourage you to use the same address. However, Bitcoin, especially because it is UTXO based and not account based, is going to really encourage you to not reuse addresses. And the reason for this is having a single address, if we're worried about anonymity, is generally a bad idea. It's going to leak information about your identity. If you've been sending transactions all of your life to the same address, well, if anyone links that address to you, they know, all right, this person has this much Bitcoin in this. It also allows people to, perhaps figure things out about you. If you are always using Bitcoin between 8 a.m. And 8 p.m. Eastern Standard Time, people might think, all right, well, this person is probably in the USA, or perhaps they're a night ride. They're a very night owl in Japan, for instance. Or anyone. Remember, everything. All of this is public on Bitcoin or in most blockchains. So if you're always paying your landlord from the same address, well, now they know they can look back and see what your how much money you have and how much they can then ask for you and raise your rent. So generating new addresses, for all practical purposes, infinite. Obviously not really infinite, but a huge number, more than anyone would be able to use in their lifetime. Why don't we try with Bitcoin to reuse these addresses? So again, other systems are less open to this. So one thing that is actually a problem with Bitcoin are these dust addresses that have such a small amount of Bitcoin that it's not even worth it to move it anymore. And this is going to take up space on the blockchain for all time. And so some other systems like Polkadot has the concept of an existential deposit. So if you have an address with less than a certain amount, 0.001 dots, for instance, then that address will simply get wiped from the network. So something like this doesn't work quite as well for other systems, but certainly for Bitcoin it makes sense not to reuse addresses. And most wallets will allow you to most wallet software will allow you to automatically just keep creating new addresses. So this is often done with a certain process called BIP32 to create hierarchical deterministic wallets. So here, we're going to generate from a single seed, we can make a series of addresses which to the outside world look unlinked, but to which the wallet software is going to have access to. We actually even can then have our transactions come from multiple addresses. Remember, we can do this when we're creating a Bitcoin transaction. We can have input different UTXOs from different addresses into a new output. So this allows us to have one seed, but many addresses that we can deterministically recreate. Okay, the last thing I really want to discuss today is splitting and sharing keys. So let's first start with a real problem here. And the real problem is my wife does not like the fact that I spent Bitcoin, bought several different cryptocurrency related sweaters. So we decided that we are both going to have veto power over our spending. So that if I think she's spending too much money on Bitcoin dresses, which she actually does have a Bitcoin dress, and I'm spending too much money on Bitcoin sweaters, we want us to have veto power. How can we do this in Bitcoin? Each have veto power over the other person's spending ability. So the naive way to do this is just take some, we're going to put all of our funds into one public address, and I'm going to have half the secret key and she's going to have the other. So I know the red part here, the 5J1 ... She has the blue part, GAZ ... And we have to put them together in order to actually sign anything. So there are, of course, a few problems with this scenario. One, it's kind of a pain. We're going to have to enter this manually. I can look over at her part of the secret key and perhaps figure some of it out. If it's going to be easier for me to crack, right? I know a huge part of what the key is. You remember how much longer it took to calculate a key or a public address based on how many characters we know? Well, I've already got half of the characters here down. I've only got half to go. So I've really reduced by orders of magnitude the amount of computation I might have to do to get access to this account and go and buy my, Bitcoin sweaters. So we can see, there are some problems with this naive approach. It does have the benefit of simplicity, however. It also, it's very limited, right? So if I were involved in perhaps a more complicated relationship where there are three of us, perhaps a group of three, or parents and children, or if we want to have some more complicated way of coming to a consensus instead of all of us having to agree. All right, so let's say here, I've got values k and n. K is less than n, less than or equal. And can we split the key into n pieces? So if we have k shares, we can determine the key. But what we don't want is we don't want any number of shares to give enough knowledge to guess the key. So what I mean by this is if I don't have enough shares to actually do the transaction, then I should be in the same position as someone not having any of these shares of the key. So can we do this? Can we do something like best 2 out of 3 people need to have this, or could we split up a key into 100 pieces? We couldn't do that with our naive splitting. We didn't have 100 characters. So one way to do this in a more complicated way is just generate some random value and XOR it, exclusive OR it, with the initial key. And then together, so we now have 2 shares. We have some R and then S XOR R. So R is just an entirely random or pseudo-randomly generated value. That's not going to help us. And S XOR R, if we don't know R, is also going to look essentially like a random value. It's only if we have R and S XOR R together that we can XOR this again and get the actual key. And we can do this just extrapolate it outwards with more XORs, more random values. But n has to equal k in this scenario. So it's really useful if you want to do 3 of 3 or 4 of 4 signing, but it really falls down. There's no way, if you're missing any of these, you're not going to be able to actually calculate the secret key. So it really falls down once we get to the point where we want to do best 2 out of, or 2 agree out of 3 or 5 out of 7 or anything like that. So what do we do if we want our k value to not equal our n value? Which we can see this actually occurring in a lot of places, right? So I want to make sure that my son gets my Bitcoin upon my death. if we decide that he has come into an inheritance, well, if both my wife and I agree that we can give this Bitcoin to my son, and if it's only going to be me and my wife, then that's fine. But what if I'm dead? Then she is not going to be able to send this. So why don't we have my lawyer has one share here. I have one share, my wife has one share. And any two of us, so if my wife dies, my lawyer and I can send the Bitcoin to my son. If my wife and I agree he's coming to his inheritance, we can both together do it. Or if I die, then my wife and my lawyer can send the funds. Or you need at least 2 members of a board to agree to spend money from a corporation's Bitcoin account. Or 5 out of 9 justices are acting to pay out Bitcoin in escrow. So we can see there are a lot of different cases where we might want to use this in real life, so in actuality. However, using our naive splitting or our XOR process, this is going to be impossible. We needed k to equal n. So there is another interesting thing based on slopes of a line, an intercept. So this is Chamir's secret sharing scheme. So the idea behind this. So let's say our secret key is 5, and I realize it's a very small number, but just to make the math easier. What we can do is send out, if we want to do, let's say 2 of 3 here, so we need 2 of 3 to agree with it. Share sub 1 gets the point 3.8, so they just know this point. Share sub 2 knows -3.2, and share sub 3 has -7, -2. So any one of these points, you're not going to be able to calculate the slope from. Right? Our slope is y equals x plus 5. Again, very simple. Imagine the numbers are bigger for a real Bitcoin address. However, if I have 2 or more points on the line, then I can calculate that intermediate value. So I can calculate 100 of these shares, but as long as 2 people have them and come together and agree, they can together figure out the actual intercept. So if you just have one point, there are all kinds of different slopes that could be coming from that point. Really, essentially, an infinite number. Although with discrete math that's modular, we do have some limits, but it's going to be essentially infinite. If you can't determine the slope, you can't determine the intercept, which means you don't know the key. But as soon as you have 2 of these, you can calculate the slope and thus the intercept and thus get the key. And you say, well, that's all very well and good, but what if I want 3 of n? Well, here we just need to increase the order of the function, of the polynomial. So here we've got y equals x squared plus 5, and I pass these points out. And the only way to determine where this parabola intercepts is if you have 3 or more points on it. So here I've got a 3 of 4 sharing scheme. By having 4 different points, as long as you know 3 of them, you're able to reproduce that parabola. Otherwise, you can't. And then we can stretch that out just with higher order functions. So we're going to determine the key, then determine k. So what is the minimum number of shares that would be needed to unlock the funds? All right, so now create some k minus 1th order polynomial which intersects the origin at 0, key. So somewhere somewhere along that line, there is along that axis rather, there is an intercept point. We then determine n random points in the function, and distribute those n random points. So here we've got this cool concept that we can now set k and n to whatever we want, and they're very easily calculated as long as you have at least k of these shares. And if you don't have k, if you only have k minus 1, then you actually don't have any additional information to help you break the code. Unlike what we had with our naive sharing scheme. So this is a really cool process, but the problem is, of course, at some point here, we are generating the actual secret key. So there are other ways that we're not going to go into here, but I just want you to know that these do exist. A way for everybody to make partial signatures. And so you never have to have the secret key actually generated until you are actually signing off on something. So you never reveal the key. Every user can sign the transaction, and the key was never produced in one single place. So what we have been talking about so far has been actually using and sending your coins yourself. But not everybody always does this. And is a good idea to keep track of your own keys, because it's not your keys, it's not your coins. However, there are online wallets, both exchanges, where somebody will keep track of this for you, and you have to trust that exchange. There are online wallets that you can access or even access online that require no installation on your part. You just need to enter in your key somehow and store that offline, and the code will work for you. So they're sort of non-custodial. But there are possible security worries when using these, but they are very, very convenient. So an exchange is not just is different from an online wallet in that they also allow you to buy and sell Bitcoin. They act just like a stock exchange. So I'll give you whatever, this much money for a share of stock, or I'll give you this much money for this much fiat money for one Bitcoin. So this is really convenient because you can buy a Bitcoin or other cryptocurrency and store it. But of course, you're offloading your responsibility. So part of the benefit of cryptocurrency is that you can verify everything. You're obviously not going to be able to do this if the online exchange is handling all of this. And there are also other risks, such as they may be fractional reserve, which means they may not have all the Bitcoin that they say they do. And since there's only a limited number of Bitcoin in the world, remember only 21 million will ever be produced, then actually slightly less than that. There are a few known instances of certainly lost Bitcoin and burned Bitcoin. So it can be a problem if you trust them to have it without proof. So, for instance, there are some risks with holding your cryptocurrency on an exchange. So first is an exchange run. So if for a regular bank, they never generally have as much money on hand as they have loaned out. So if enough people ask for that money back, then the bank might not have enough cash on hand. If rumors then spread that the bank doesn't have money, everybody goes to try to cash out, causing even more of a problem. So in the United States and many other countries, bank accounts are backed by something. So for instance, the Federal Depository Insurance Corporation in the US, this shouldn't happen. So if a bank does fail, anyone that has a bank account is going to get up to, I think, $250,000 reimbursed. But this is because the government can always print more money, but you can't print more Bitcoins. So you can imagine this could be more problematic. It could be that this is an exit scam, that this exchange isn't really running Bitcoin, isn't planning to give it back to you. There have been several cases where founders have run off with the Bitcoin in an exchange. And even for some of these, it seems like everything is working because people get their Bitcoin back by others who are depositing Bitcoin at first, but eventually these Ponzi schemes will eventually fall apart. And finally, a hacker could break into the exchange's software. They could hack into their account and move all the Bitcoin. And if that happens, there's no CEO of Bitcoin to figure out, oh, right, this was stolen from this person. Remember, our concept of ownership is, do you have the private keys to that address? And if someone takes those private keys from you, moves it to a different address, well, according to the rules of Bitcoin, I'm not talking about morality here, I'm just talking about the internal rules of or legality, just the internal rules of Bitcoin. Bitcoin considers that to be yours. You have the right to do with it what you want. And a hacker could also break into your own computer software, and in fact, it might be up to you. Do you trust the exchange operator to take better control of your keys than you yourself would? But there's certainly exchanges are sort of painting a target, right, to be attacked, because that's where all the Bitcoin is, right? So there's a famous line supposedly said by a bank robber when asked, "Why do you rob banks?" Well, that's where the money is. So why would you try to rob exchanges? That's where the Bitcoin is, not in some account with 1/10 of a Bitcoin in it. But if you can access one of an exchange's accounts that may have millions of dollars worth of Bitcoin in it, they're certainly going to go there. So thank you. Hopefully this has given you a better idea of the process of using Bitcoin and other cryptocurrencies.